Okay, hello everyone. My name is Lei from Boston University. I will talk about CAPSys, Contention-aware task placement for data stream processing. So this is a joint work with my co-authors Yuanli, Zikun, Vasiliki, and Ibrahim from Boston University. So stream processing has been a well-adopted technology for low latency data processing and continuous analytics. All major cloud providers provide managed services for stream processing in support for a wide range of applications. So, however, managing the streaming service is challenging. So thanks for Professor Matt. We already have some background for stream processing, but here we will just focus on the deployment step, how we deploy the streaming data flow. So we start from the logical data flow. So each vertex in the logical data flow represents an operator that defines a specific processing logic. So here in this example, we have a source and sink, and a stateless transform operator followed by a window aggregation operator. And to deploy the job, we need to translate the logical data flow to a physical data flow by assigning the parallelism to each one of the operator. So here, each vertex in the physical data flow represents a task that is the smallest scheduling unit. And next, the task placement step will map all the tasks to the computing slot in physical workers, where each computing slot is like a physical thread. And all streaming tasks are long-running, so we only need to do this deployment once at the very beginning. So in this work, we focus on the task placement step, and we show that task placement can greatly affect the execution performance and has been a factor that is overlooked in the past. So to be more specific, we used the following example to explain why task placement will affect the performance. And in this physical data flow, we assign the parallelism 2581 to each one of the operator, and we want to deploy this totally 16 tasks to a cluster of 4 workers, where each worker contains 4 computing slots. We exhaustively explored all possible AT placement plans, and we sort them based on the achieved throughput. And here in this figure, we show the best 3 plans and the worst 3 plans. And as we can see, under the same amount of resource allocation, by simply changing the task placement plan can get us up to 40% performance difference. And to show why this happens, we show one of the good plan P1 and one of the bad plan P4. So for the bad plan, it co-locates all the window aggregation tasks on the same worker. So this window aggregation operator is a stateful operator that has very heavy state access pattern and it causes very high disk I/O resource usage. So this resource contention causes this performance degradation. Well, for the good plan, we balance all the resource-intensive tasks across all the workers and have a much better performance. So from this simple observation, our takeaway here is that a good placement plan should always balance resource consumption across all the workers. So before jumping to the solution, here are the limitations for existing approaches. So most streaming processors has the task homogeneity assumption. So we will use the Apache Flink as example. It provides this default and evenly policy as built-in strategies for task placement. For the default policy, it will just try to fill up all slots of one worker before the next one. However, the order of which worker is going to be deployed first or which operator will be deployed first is determined at random. For the evenly policy, the difference is it will try to balance the number of tasks among all the workers. However, the order for which worker or which operator to be deployed first is also determined at random. So both approaches are non-deterministic. So multiple runs of the same deployment can lead to completely different random plans. Well, the second limitation is for the set of solver-based approach. And the representative approach here is the ODRP algorithm, which formulates the task placement problem as an integer linear programming model. And the problem is it takes a very long time to find the global optimal solution. Actually, for the previous example, it takes 26 minutes to generate the results. So for the ideal approach, what we want to have is we want to consider heterogeneous task characteristics so we can balance the resource usage, not just the number of tasks. And for the decision-making process, we want it to be very, very fast so we can support online setting where frequent reconfigurations are required. So therefore, we propose CAPSys, and our contributions are as follows. we propose a contention-aware placement search algorithm that exploits empirically verified heuristics to prune the vast search space. And secondly, based on this, on top of this search algorithm, we implemented an adaptive resource controller, an end-to-end solution for streaming data flow deployment. So CAPSys considers both auto-scaling and task placement in concert with a full integration into Apache Flink. So we first look at how the search works. So based on the motivation study, our target here is to find a placement plan that can minimize resource usage imbalance. So how do we quantify this imbalance? The key idea is to define the cost value for any given placement plan as the ratio of its bottleneck worker resource usage to the ideal resource usage. And I will explain what do they mean by this example. So in this physical data flow, assuming we assign the cost value to each one of the tasks in this way, and specifically we consider CPU, disk I/O, and network bandwidth consumption. But for simplicity here, we just assign like a single dimension cost to the task. And given the placement plan F, now we explain what is the bottleneck worker resource usage. So we just calculate the resource usage for each one of the worker by summing up all the tasks deployed on each one of them. And here we can see among the three, worker 2 is the most expensive one. So worker 2 is essentially the bottleneck worker here, and is most likely to cause resource contention and lead to performance degradation. To calculate the ideal resource usage, we just use the total task resource usage divided by the number of workers. And here it represents the theoretical perfect balance scenario where all the resource usage are evenly split to all the workers. So here the ratio of 12/9 gives us the specific cost value for this task place plan F. And actually this ratio represents how a placement plan deviates from the perfectly balanced case. So a smaller value is better, where 1 indicates the optimal value, and we want to find a task placement plan that is as closer to 1 as possible. So now we explain how we search and prune the search space. So essentially, we just apply a simple depth-first search process with a tree structure, and each layer of the tree, we explore a single operator. So for, assuming we start from the source operator, so it turns out there are only 2 options to deploy 2 source tasks. We either co-locate them on the same worker or separating them on different workers. If we use this node on the right side to continue the search, then we have 3 more options to deploy the transform operator, 2 more options to deploy the window operator, and 1 more option to deploy the sync operator. So we are incrementally adding more tasks to the placement plan, and all the leaf nodes at the bottom layer represents all the possible placement plans. So based on our cost model, not only we can assign this cost value to the leaf nodes, but we can also calculate this cost value to each one of the partial placement plan. So the key observation here, so if we use this rightmost search path as example, we can assign C1, C2, C3, C4 to each one of the nodes. So the key observation here is this cost monotonically increases at each layer of the tree. And the intuition is as we're adding more tasks to the task placement plan, the bottleneck worker resource usage can only monotonically increase. So this observation enables us to safely prune the branch once the cost exceeds some certain threshold. So our solution is essentially just to introduce such a configurable threshold alpha such that when the cost of any partial placement plan exceeds the threshold, we prune it right there. So as an example, if co-locating 3 window tasks on the same worker exceeds lead to the threshold violation, then we're gonna cut the branch right there and avoid further exploration in the following layers. And it turns out this simple technique can aggressively reduce the size of the search tree by orders of the magnitude. And following on that, we further introduce a threshold auto-tuning process, which can automatically find threshold values to effectively prune the search space. And another technique we use to prune the search space is to reorder operators based on their resource usage. So we prioritize the operators with higher resource usage, so we can explore them earlier in the search tree in the first few layers to enable early pruning. And for details, please refer to the paper. And on top of this search algorithm, we present CAPSys as an adaptive resource controller that considers both auto-scaling and task placement in concert with for integration to Apache Flink. So here shows a workflow for CAPSys. So starting from the left side, we have the Flink job manager and the Flink task manager as the workers here. So assuming we already have a job up and running, so the first step here is for the metric collector to collect the runtime information from the resource cluster and build this job profile, which includes what is the resource usage for each one of the operator. And the second step, we send this job profile to the scaling controller, which makes the scaling decision. So here we implement the scaling controller using DS2, which is state-of-the-art auto-scaling policy for streaming data flow. And following on that, we send this physical data flow to a placement controller, which we invoke a threshold auto-tuning process along with the CAPS search procedure to get us a good performing placement plans. And at the end, we just update the job through this custom scheduler we implemented in Flink Job Manager. So as a result, CAPSys provides an end-to-end solution for streaming deployment, streaming data flow deployment, which we can automatically trigger rescale operations and establish the job profile and optimize auto-scaling and task placement at the same time. So now comes to the evaluation. We use EC2 instances as the workers in our experiments, and we select a wide range of queries with diverse workload characteristics. Most of them are from the Nextmark benchmarks. So some operators are compute intensive, some are disk IO intensive, and some are network bandwidth intensive. So in this talk, we'll just show the comparison between CAPSys and the Flink strategies and show how CAPSys performs along with auto-scaler. So first, we compare CAPSys with Flink strategies. So just as a recap, Flink provides the default and evenly policy with a very high randomness in the decision-making process. And we repeat each approach 10 times to capture that variation. So in this figure, we show the performance matrix for throughput, back pressure, and end-to-end latency for one of the query. It's a window aggregation query here. And note that the back pressure here means the percentage amount of time the source operator is flow controlled by the downstream. So a lower value is better. We start from the throughput, and this top green dashed line indicates the target throughput. So CAPSys can consistently achieve the target through actually up to 6 times higher than Flink strategy. Well, for Flink policies, it shows a very high variation across 10 different deployments. And similar for back pressure and end-to-end latency, CAPSys can achieve the best performance. So here we just very quick show all the results for the full set of queries in our experiments, and only CAPSys can consistently achieve high performance across all queries compared to Flink strategies. So next we show how CAPSys performs with the auto-scaling policy. For the setup, we periodically vary the input rate between a high and a low value. And here the yellow dashed line just indicates how we vary the target input rate over the timeline. So the blue line now represents actual achieved throughput, and each vertical dashed line indicates a rescale operation. So as we can see, CAPSys can take much fewer iterations to converge in response to the target rate changes. And what is not included in this figure is that actually CAPSys requires less amount of resources to achieve the same target rate. And the takeaway from this experiment is a better task placement plans can actually make auto-scaling decisions more accurate. And the intuition is we don't really need to scale up if a better task placement can already resolve the problem and achieve the target throughput. And more experiments, please refer to the paper if you are interested. To summarize, we propose contention-aware placement search, which uses empirically verified heuristics to efficiently optimize the task placement problem. And on top of this algorithm, we implement CAPSys, an adaptive resource controller, or an end-to-end solution for a streaming data flow deployment that considers both auto-scaling and task placement in concert. And finally, CAPSys achieves consistently higher performance and lower decision time compared to Flink and solver-based strategies. So that's the end of my talk. Our code is available online. Thank you so much for your attention.